Welcome, everybody, to Skeptics in the Pub Online. This is our first ever talk in this new series of weekly talks that we're doing whilst everybody is in lockdown. Skeptics in the Pub Online is a production of a collaboration of the various Skeptics in the Pub groups across the UK. Our talk in particular this evening is brought to you in collaboration with the Portsmouth Skeptics, because our speaker this evening is the honorary president of the Portsmouth Skeptics. Welcome, everybody, to this event. Hopefully you can all see everything. Feel free to introduce yourselves in the chat, to say where you're from. I know that we've had a lot of people talking about how they're viewing this from Israel and from New Zealand and from America. So clearly we have quite a lot of international attendees, as well as hopefully our regular UK Skeptics in the Pub folk. The format of the evening is going to be very much like your normal Skeptics in the Pub talk, except I'm not going to be drinking beer. I've got a cup of coffee here instead, so it'll be slightly poorer for that reason for me, but the rest of you can have a wonderful time, I'm sure. The talk is going to be about an hour's length, something that kind of region. Then we'll have a short break before we'll come back for a Q&A. Because this event is being put on by a collaboration of the Skeptics in the Pub online groups, in the Skeptic in the Pub groups from the UK, we've actually set up a small donation link that if you enjoy the talk this evening, you can put a little bit of a donation into our PayPal there, and that'll just help us cover the costs of streaming this and the various kind of services we need to sign up to make this whole thing work. The other thing you'll see popping up in the chat semi-regularly is a link to Slido, which is the website where we'll be encouraging you to not only submit your own questions, but also to say which questions you'd like us to ask during the Q&A. So feel free to pop along to that website and just see how that works. And you can see any questions that get asked there. You can upvote and downvote the ones that you think really need to be put to our speaker once the talk is finished, and which ones we think are less of a priority. Feel free to chat during the talk as well. But other than that, I think we're ready to hear from our fantastic speaker, the first speaker of the Skeptic in the Pub online series. He's a name and a face that is very, very familiar to anybody who's involved in anybody who's a fan of British science. If you watch a lot of science programming on the BBC, you'll know his face. If you listen to a lot of science programming on the BBC, you'll know his voice. Here to talk all about the world according to physics is, please welcome Professor Jim Al-Khalili.
Well, hello everyone. Good evening. First of all, an apology. If there was a long delay between me saying hello after Marsh introducing me, that's because my line is really poor. And so there's a really long delay. I'm hoping you could all see my slides, hear my voice, enjoy the lecture, even if, things are rather out of sync. Well, so here we are. Welcome, fellow skeptics. I want to talk to you about, well, in fact, I'm not doing this to flog my latest book, but, hey, if you want to buy it, please go ahead. I want to talk about my love affair with physics and what we know now in 2020 about the physical universe. So the world according to physics is my ode to physics, to the subject. I like to think of our knowledge of the physical universe as an island, right? And it's surrounded by an ocean of the yet to be understood, the mysteries, the yet to be explained phenomena. We don't know everything, right? As we expand our knowledge, so the island grows outwards into the sea. There are a lot of fantastic books on popular science, on physics out there now, which really, cover the breadth of the subject and give the history of the subjects. Essentially, they're an exploration of this island of our knowledge of the physical universe. This book, The World According to Physics, is more a trip around the shoreline. It's at the boundary, the frontiers of what we know, and maybe wading out a little bit into the water to explore some of the phenomena and mysteries out there that we know in the universe that we've yet to understand properly and yet to explain. Now, in writing this book, it's a small book. It's just like a pocket-sized book. I'm really delighted with the feel of it. I've had a lot of colleagues and fellow physicists help me with various issues here and there in areas outside of my expertise. And one of them is my colleague in the physics department at the University of Surrey, Justin Reed, who's an astrophysicist and expert in dark matter. And obviously he helped me, so I gave him a copy of the book, and suggested that a better title to the book might be this one: The World According to Jim Al-Khalili. And now, I am far too modest to ever contemplate this being a good idea, but I have to say that's quite nice, because I do get a bit polemical, opinionated in places in the book, and giving my view of the status of physics. Now, let me just go back, guys. That's a bit too arrogant to show that slide. A lot of people's understanding of their world comes from religious faith, different religions, different ideologies, different outlooks on life. Maybe people reach some sort of understanding through meditation. For me, science, the scientific method, and physics in particular, is I don't want to come across as arrogant, but it's the best way of understanding the true nature of reality, the true nature of the physical universe. Physicists, scientists don't like to say we are certain about anything. We always have to have doubts. We always have to be open to changing our minds in the light of new evidence or new experimental data. But there are certain things about our world that we are extremely confident about. Take the force of gravity. I know if I were to drop a ball from a height of 5 meters on Earth, then physics tells me that ball will hit the ground after 1 second. Not half a second, not 2 seconds, and it doesn't change from day to day, but anywhere on Earth, if I drop a ball from a height of 5 meters, as near as damn it, almost exactly, it'll hit the ground after 1 second. No ideology, no religion, no amount of meditation would ever tell you that ball would travel through the air for 1 second before hitting the ground. That's a simple use of a mathematical formula first developed, in fact, by Galileo. So there are truths about the world that are part of the reason why I have so fell in love and still have a passion for this subject, particularly as a theoretical physicist. Because for me, there's nothing more profound than writing down Greek symbols, algebra on a piece of paper, and it gives me a number, it gives me some result that when I go outside into the real world and check and observe and measure, it turns out that mathematical answer was correct. That the universe speaks the language of mathematics, and we can decipher that language. We can learn about reality by scribbling equations on a piece of paper. That blows my mind. Right. Okay. Well, let's get started. So this is the title of a paper by Stephen Hawking. Now, it was published in 1981, in which Stephen Hawking suggested that we were coming to the end of physics, the end of theoretical physics, that the mathematics describing the laws of nature, all the phenomena in the physical universe were pretty much wrapped up. In fact, if I highlight the first paragraph, he says, in this article, I want to discuss the possibility that the goal of theoretical physics might be achieved in the not too distant future, say by the end of the century, end of the 20th century. By this, I mean that we might have a complete, consistent and unified theory of the physical interactions which describe all possible observations. What Stephen Hawking's talking about here is the so-called theory of everything. The one equation that is so compact and neat you can stick it on your t-shirt, and that equation describes all the forces of nature, all the phenomena, the physical phenomena. It doesn't describe everything. When I say theory of everything, I don't mean it's going to describe human consciousness or human behavior or economics. No, the physical universe. Well, Stephen Hawking, in writing that in 1981, I think physicists would now agree, was overly optimistic, because it doesn't look like the end of theoretical physics is in sight. We still seem to have a long way to go. In fact, that attitude that that physics was coming to an end at the end of the 20th century was something that physicists thought was going to happen at the end of the 19th century as well. 100 years before this, or say, around about 1890, physicists thought again that physics was coming to an end. We were able to understand all phenomena. We had Newton's mechanics and his law of gravity. We had Maxwell's theory of electromagnetism and light. We had thermodynamics and statistical mechanics. But what else is there? We understand the whole universe. And then by the mid-1890s, we discover X-rays. We discover radioactivity. We discover the electron, the first elementary particle. A few years later, 1900, and the whole new revolution in physics kicks off. Max Planck comes up with the very first equation of quantum theory, describing how heat given off by hot bodies actually comes in tiny lumps, we call quanta. Einstein develops his theory of relativity. He also helps develop quantum theory. Then you get quantum mechanics. And so what we still call today, even though it's 100 years old, we still call it modern physics, actually overthrew a lot of the ideas of 19th century physics, showing that we were very far from the end. Similarly now, and the sort of stuff that I talk about in my book, I believe we are still some way away from the end of theoretical physics, because new ideas, new phenomena, new discoveries are being made. And the promised, the hoped for theory of everything seems to be as far away as it was 10, 20, 30, 40, 50 years ago. Now, if we think about let's talk about the big discoveries in the 21st century. Here's a couple of examples, probably the two most celebrated examples. There's the discovery of the Higgs boson in 2012 by the Large Hadron Collider. And there's Peter Higgs, who had postulated that this particle should exist, and it was finally confirmed at CERN. Then a few years later, of course, there was the very first detection of gravitational waves. These are ripples in space itself that travel through the universe, that emanate from a very cataclysmic disturbance in space. In this case, the collision and merger of two black holes. Now, obviously, this picture here is not drawn to scale. Those black holes aren't just like near the moon. In fact, those black holes collided over 1 billion light years away. So it's taken light and indeed gravitational waves, which also travel at the same speed, the speed of light, it's taken them 1 billion years to reach us. Now, that collision of the black holes is a bit like dropping a stone in a pond. Imagine it's a very large pond. Dropping the stone in the middle, you'd see concentric rings radiating outwards to the edge of the pond. Now imagine those rings are ripples, oscillations of the water, of the surface of the water, but it's energy being transmitted outwards. These gravitational waves are oscillations or disturbances in space itself. Now, I mention these two examples because, in fact, they're not really that exciting. I mean, okay, look, they made headlines and they're rightly celebrated, and Nobel Prizes all round, basically. But the Higgs boson was predicted by Peter Higgs and others half a century ago. So it wasn't a surprise that we discovered it. It would have been more of a surprise if we hadn't discovered it. And gravitational waves were predicted by Einstein 100 years ago. So again, no one who understood Einstein's relativity was in much doubt that gravitational waves do exist. It was simply a matter of building that were sensitive enough to pick up these tiny, tiny ripples in space. Now, they're tiny, despite the fact that two black holes colliding is a pretty big thing to happen. But because they're so far away, it's like dropping that stone in the pond. If the pond is very big, by the time those ripples reach the line, they've almost disappeared. And so that was the case of gravitational waves. So finally we detected them, but we were sorry. These were almost box ticking discussions, things that we already expect. There have been other mysteries that we are still trying to get around. Probably the biggest, most unexpected discovery in physics took place in 1998. Now, this is my little picture to describe it. Is this the discovery of something called dark energy? It's almost entered popular culture now. Dark energy, dark matter. People may not know exactly what it is. Well, actually, physicists don't know exactly what it is yet. But it's certainly something that captures the imagination. Dark energy, well, the name, I guess, doesn't really do it justice. It's a form of energy, but it's something that we're now realizing is controlling the fate of our universe. You see, we've known since the late 1920s, thanks to the astronomer Edwin Hubble, that space is expanding. Our universe is getting bigger. Okay, the distance between galaxies, that space between them, is stretching. We have developed theories to describe the nature of the universe, what we call cosmology, and we now have pretty solid evidence that the universe began in what we call the Big Bang. We've understood that the universe has been expanding ever since, but it was set in motion. This expansion was caused by the initial conditions at the very early moments of the universe. Effects of gravity due to all the stuff, all the matter in the universe, should be putting the brakes on the expansion. It should be slowing it down. A bit like stretching a spring, and you reach some point when you can't stretch it anymore and it collapses in on itself. And that was a particular scenario that many astronomers and cosmologists thought was the way our universe was, that one day it would reach maximum expansion and then gravity would win and pull everything back in on itself, and it'll recollapse in what we call the Big Crunch. But they thought, if there's not enough stuff in the universe, maybe it won't be able to stop it and cause it to collapse in on itself. Maybe it'll just slow it down so that it doesn't expand so fast, or slow it down so it doesn't expand at all and just hovers, not expanding, not collapsing. Until 1998, when astronomers studying the way very, very distant galaxies are moving away from us saw that they were moving away faster than they should be. Basically, that the universe's expansion, rather than slowing down, is actually speeding up. And that's why they came up with this idea of dark energy, this mysterious force of anti-gravity that somehow was winning the battle against gravity. Gravity's trying to pull everything in, dark energy is pushing it all out. And as the universe reached a certain size, when the matter was so far apart that its gravitational pull on each other, on everything else, became too weak, that's when dark energy kicked in and started winning. And so, completely unexpected, but now we believe that the universe's expansion is getting faster and faster. We assume if this carries on like this, it'll end in what we call the heat death of the universe, which is a rather boring and depressing future. But bear in mind, this is trillions and trillions of years from now, so we don't have to be panicking just too late, just yet. So dark energy is a mystery that we haven't really, we're starting to get an idea for its origins, something called the quantum vacuum. It's probably where dark energy comes from. But there are other mysteries that we haven't understood. Something else with the word dark in it, dark matter, which you should not confuse with dark energy. Dark matter has nothing to do with dark energy. Dark matter probably should better be called invisible matter. We know it's out there. There's much more of it than there is of the normal matter, made of atoms and the stuff that we can see. We know it's there, even though we can't see it, because it still influences us through its gravitational force. So dark matter has a gravitational pull. It's attractive gravity, not like dark energy, which is like repulsive gravity. Dark matter holds galaxies together. Dark matter was essential in the formation, the creation of galaxies in the very early universe in the first place. We know it's there. The mystery is we don't know what it's made of. It can't be made of any normal stuff that we already know. It can't be made of any of the elementary particles we've already discovered. It must be made of some new particle yet to be discovered. And the hope has been, and still is, that just like we discovered the Higgs boson, in a particle accelerator, we might discover a new type of particle that is the ingredient of dark matter. But we're still looking. So this, and there are other mysteries, like there's something else not to be confused with dark matter, which is antimatter. We know antimatter exists. That's not, we know what it's made of. What we don't understand is why there isn't much of it about. It's sort of lucky for us there isn't much antimatter about, because antimatter and matter will annihilate each other and we'd all disappear in a puff of energy. So it's good that there isn't much about. But we think that the same amount of matter and antimatter should have formed in the early universe. So where has all the antimatter gone? There are even more questions, which I will come to later on in the talk, showing that actually we're a long way from answering all the questions about the nature of the universe. Pleased with this slide. This is my favorite slide in this talk. It took me a long time, a whole evening of messing around with PowerPoint to produce this. I'm very proud of it. I just hope the resolution is good enough on your screens as you're watching this to be able to read the words. Throughout the history of physics, certainly, we've been on a quest for unification. Now, this is we have discovered that seemingly unconnected phenomena, unconnected concepts in physics or properties of the world actually turn out to be different aspects of the same underlying more general principle or more general phenomenon. So gradually, all the different forces and the different fields and the different mechanisms of the universe, we're seeing they're connected to each other. And there's a simplification that comes from this idea of unification. Obviously, the ultimate, the Holy Grail, is to unify everything together into that Holy Grail, that theory of everything. So here's, in one slide, the history of unification. I start, see, this is what I mean by the words being very small, top left, and they're deliberately in that size font because I'm going to fill this slide up. Falling apples, orbits of planets. Yes, you've guessed it, that was Isaac Newton. Isaac Newton sitting supposedly under the apple tree on his mother's farm in Cambridgeshire. He realized that the apple falling to the ground was being pulled by the same force as that which keeps the moon in orbit around the Earth and the Earth in orbit around the sun. It's the force of gravity. We now take that for granted. It's gravity that pulls the apple. It's gravity that keeps us in orbit around the sun. But until Newton came up with his law of gravitation, that was far from obvious. Scientists, physicists, scholars thought that the laws of here on Earth, there's no reason why they should be the same as the laws governing the behavior of the heavenly bodies up in the sky. Next, mid-19th century, we have electricity and magnetism. Thanks to Michael Faraday, working with electric fields and electric currents and magnetic fields and light bulbs and so on. James Clerk Maxwell, the great overarching force called the force of electromagnetism. I always remember my, sorry, I'm just going to quit my email window because it just pinged. Not that I'm going to get that many emails this time of the evening, but just in case. I remember as a student studying physics in my second year as an undergraduate in electromagnetism classes, and the lecturer started with what are called Maxwell's equations. Equations involving quantities called vectors describing electric fields and magnetic fields. Now, you might think electricity, that lights your room, the electric currents, don't have anything to do with magnetism. although you may remember from school something called an electromagnet. You can create magnetism from coiling a wire and running a current through it. Well, in this lecture, my through a few steps of algebra and arrived at a quantity which is in fact the speed of light. And he says that's where Maxwell realized that light itself is oscillating electric and magnetic fields traveling through empty space. And I remember that moment was a shiver, honestly, a shiver down the spine moment when you see a connection just through doing algebra, connecting electric and magnetic fields to the speed of light. So that's another unifying concept, electromagnetism. Right, jump to the bottom. Heat and energy and a field called statistical mechanics connected together again in the late 19th century to give us a field called thermodynamics. Jump up, space and time. No prizes for guessing who unified space and time. Yes, Einstein in 1905 developed what we call now the special theory of relativity. So that's the theory that says time is the fourth dimension and E equals mc squared and nothing travels faster than the speed of light and all that stuff. Einstein then 10 years later combines his special theory of relativity, he generalizes it to include a new picture of gravity. So he gives a more profound, more deep understanding of the meaning of gravity than Isaac Newton did. And he develops what we now call his general theory of relativity. So for Einstein, gravity isn't this invisible force, the invisible rubber band that pulls the apple towards the Earth or that holds the Earth in orbit around the sun. For Einstein, gravity is the shape of space and time. Now I can say the words, but to understand the concept of how gravity describes the shape of space and time is really quite a difficult concept to get your head around. General relativity, however, kick-started a whole new area of science called cosmology. Cosmology, the modern cosmology, which is basically the structure and shape and origin and lifetime of the entire universe. The whole universe, it turns out, not just the apple falling to the ground, not just the Earth in orbit around the sun, but the whole universe's evolution is governed by Einstein's general theory of relativity, his theory of gravity. Right, so let's back to the slide. I promise you I'm going to fill this all up. Right, down to near the bottom, atoms. By the beginning of the 20th century, the existence of atoms was confirmed. By the end of the first decade, Ernest Rutherford had carried out the first experiments to look at atoms, see that they were mostly empty space. They had a tiny nucleus in the middle with electrons buzzing around the outside, like a miniature solar system. And looking inside the atom, it was understood that there must be glue, there must be forces holding the nucleus together. And that gave an understanding of nuclear forces. Right, jump up. Again, beginning of the 20th century, as I mentioned at the start of my talk, quantum theory is developed. Max Planck, Albert Einstein, and others developed this idea that down at the tiniest scale, at the level of atoms, energy and other properties come in lumps, come in discrete bits. They're not continuous. By the mid-1920s, quantum theory has developed into a fully fledged idea we now call quantum mechanics. Quantum mechanics, one of the most profound, probably the most important theory in all of science. Quantum mechanics describes the world of the very small in a way that Newton's mechanics or Einstein's relativity describes the world of the very large. And they're very different rules. Nature behaves very differently on those two scales. Right. Next, by the end of the 19th century, the end of the 1920s, the English physicist Paul Dirac combines quantum mechanics with special relativity. And he gives us what we now call quantum field theory. He then combines quantum field theory with electromagnetism. And by the 1940s, a new theory the quantum theory of electromagnetism, the quantum theory of light is developed, and we now call that quantum electrodynamics. So that is a quantum theory that describes one of the forces of nature, electromagnetism. Right, jump down, the nuclear forces. We realized there were two types of forces inside the atomic nucleus, unimaginatively called the strong force and the weak force. They are described by quantum mechanics as well. In fact, by the latter half of the 20th century, quantum field theory is used to give us a better picture of the strong nuclear force. You don't have to remember all of this, but I know there's a lot of information here. But we end up with a theory called quantum chromodynamics. So that's the quantum theory of the strong nuclear force. That's the second of the forces to be quantized, as it were. Soon after that, the weak nuclear force is unified with quantum electrodynamics to give a theory called the Electroweak Theory. So now we have three of the forces of nature. And by this point, we understood there are only four, right? There's the strong nuclear, the weak nuclear, electromagnetism, and gravity. Three of them are described by quantum field theory. And together, these two theories, electroweak theory and quantum chromodynamics, give us what we now call the standard model of particle physics. It's the sum total of everything we know about the building blocks of the universe, the world of the very small, described by quantum mechanics. It's not complete. The standard model isn't the last sort of chapter in this story, because it's not really a unification of the electroweak theory and quantum chromodynamics. It's more of an umbrella term that encompasses two different theories. We are still looking for a theory that really unifies the electroweak and theory and quantum chromodynamics, a theory of all three forces at the quantum scale. That will be, we tend to refer to that as a grand unified theory. We're still looking for it. Right, now jump up to the top. Where do we leave general relativity? Cosmology leads to what we now call today the standard model of cosmology. If you can make out those letters after that, it says lambda CDM. Lambda, the Greek letter lambda, stands for a quantity called the cosmological constant, which was first suggested by Einstein, and it looks like it's playing a very important role now in cosmology. It may underpin our understanding and explain what dark energy is. CDM stands for cold dark matter. So the standard model of cosmology includes dark matter and dark energy, but again, in a rather loose way, because we still don't quite understand them properly enough. And in any case, what we really want, to get a really complete understanding of dark matter and dark energy, we need to unify these two standard models. We have the standard model of everything we know about the world of the very small, the standard model of cosmology describing the world of the very large. What we're looking for, what Stephen Hawking was hinting at in his paper in 1981, was this theory of everything, a theory of quantum gravity. Why quantum gravity? Because it's a theory that brings together quantum mechanics and Einstein's theory of gravity, his theory of general relativity. But we're not there yet. My hunch, and it's not just my hunch, a lot of physicists would agree with me, is that we're probably missing a trick by trying to combine just general relativity and quantum field theory. Remember that, right down the bottom, thermodynamics, it sort of seems to be hanging there, not doing anything. Maybe thermodynamics is the third pillar added to quantum field theory and general relativity that is required in order to give us a complete picture, the theory of everything. And maybe there are other areas that we're still, new areas of physics that we're still researching into that may also feed in. So, for example, quantum mechanics has also led to a whole new area called quantum information theory, quantum computing. There are other, I've looked down in the bottom corner, I've added another word, nonlinear dynamics, complexity theory, non-equilibrium thermodynamics. There's a lot yet to do. All those dashed lines on this slide are things that we haven't quite figured out yet. We sort of know where we need to go, but we haven't reached that theory of everything yet. Now, there's my unification slide. Where are we at? What are the predictions? What are the front runners for a possible theory of everything? Well, I depict this here as this battle between two superheroes. Well, it's an arm wrestle. It's not really a battle. That's very boring. They're not really doing much. On one hand, you've got superstring theory. I don't want to say too much about string theory, other than to say it was developed first in the in its current form in the 1980s, and then further in the 1990s. Say too much about string theory, other than to say it was developed first in the in its current form in the 1980s, and then further in the 1990s. And it is, I guess, still certainly in terms of the number of physicists investing their effort, intellectual energy and time, it's probably the theory that people hold out most hope for being the ultimate theory of everything. It's a very powerful mathematical theory. If you've heard anything about it, superstring theory is a theory that suggests we have more than just our 4 dimensions, 3 of space and 1 of time, but a theory in 10 dimensions. In fact, its most recent incarnation, developed by Ed Witten in the mid-1990s, is called M theory, where the M can stand for mother theory, magic theory, membrane theory, because the suggestion is that rather than just string theory being everything made of tiny strings, maybe they're 2-dimensional, maybe they're membranes, surfaces. I'm not really explaining string theory to you very well, and I don't have the time to go into it. But just to say, it's shown its success in being a very powerful and useful mathematical technique. In fact, it's feeding into other areas of physics. However, 2 things to say about it. Firstly, we don't yet know, it may be very pretty maths, but we don't yet know if it really is the way the universe behaves. Is it the correct description of nature? We don't know. And secondly, it suffers from the problem that we don't know how to test it. Now, a scientific theory is one that we should be able to check and test and falsify and carry out an experiment to see if it makes predictions that agree with observations and measurements. We don't know a way of doing that for string theory yet. Some physicists have been very critical about string theory, saying, well, it's not even proper science. I wouldn't go that far. I mean, I'm not particularly a fan of string theory, but then I don't work in it, nor do I have anything against it. It's very powerful mathematics, yes, but I think it's going to take some time before we're able to say something more about it. The other superhero is a rival approach called loop quantum gravity. Again, it's very difficult. It's very mathematical, it's very elegant, it's very beautiful, but we don't know if it's the correct description of nature. So these 2, and there are other approaches that are potential candidates for a theory of everything. They may or may not be right. Well, maybe then it's time to go back to the drawing board. Maybe it's time to pull back and see, well, where are we going wrong? Do we have to change quantum mechanics? Do we have to modify Einstein's relativity? Do we have to scrap both and start again? Are we missing ingredients like thermodynamics? So there are concepts that are very profound that I think we still have to space. Take an empty cube, a box filled with nothing at all, a vacuum. So it hasn't got anything inside it, but empty space. Is that space real? Does it exist? What if I were to remove the walls of the box? Does that space still exist? Or did it only get given existence by virtue of being within the walls? What if this box is inside a larger box, also empty, vacuum? And what if now I remove the walls of the smaller box? Does the space that it contained now have a more definite reality because it's part of the larger volume of empty space inside the larger box. This might sound like metaphysics, philosophy. It's not real science. But scientists have grappled with this idea of what space is for many hundreds of years. Isaac Newton believed that space was real. It was a thing. It existed independently of the stuff, the matter inside it, or the walls around the box. Newton said, space has to exist. That's where stuff happens in. You have space first, and then stuff happens inside it. Other thinkers, like the Greek Aristotle, like René Descartes, believed that space wasn't real. It only existed because there was matter, because there were particles, and you can talk about the space between them. If the universe was devoid of anything, any energy or matter, the universe wouldn't exist because there'd be no space. So who was right? Well, it turns out they were both. Both views are sort of right, according to our current understanding of the meaning of space. This is Einstein's book, Relativity, the Special and General Theory. He first published it in German in 1916. It again then got translated into English and other languages. And what's beautiful about it is that over the years, rather than rewriting it and coming up with new editions, what Einstein would do as he clarified his own thinking about the meaning of reality is that he would add appendices to this book. So the final edition in 1954, the year before he died, he added his famous fifth appendix. Just a few pages of some of the most profound ideas in physics, probably the most profound ideas that any human mind has come up with. In it, he gives his best guess at what space really is. Because in Einstein's general theory of relativity, he says, so the Einstein's general theory of relativity, basically think of it as an equation, right? And I don't have to tell you what's in the equation, just that an equation has an equal sign in the middle. Something equals something else. In Einstein's equation, he has space-time on one side and stuff, matter and energy on the other. And the equating them together tells us the curvature of space-time tells matter and energy how to move, how to behave. So they are inextricably linked. You cannot have space-time without matter and energy. You can't have matter and energy without space-time. So he says, these are two quotes from his appendix. If we imagine the gravitational field to be removed, by gravitational field, he means matter and energy, because matter and energy creates a gravitational field. But he says that gravitational field is not like a magnetic field. It is quite literally space-time itself. He says, if you remove the gravitational field, there does not remain any space-time at all, but absolutely nothing. And here again, he says, space-time doesn't claim existence on its own, but only as a structural quality of the gravitational field. So on the one hand, he says, Aristotle and Descartes are right. Without matter and energy, there is no gravitational field, and that gravitational field is space-time. So there would be no space, there would be no time without matter and energy. But he also tells us that Newton was partly right in that space is a thing. It's real. It has structural quality. It is the gravitational field. It can be bent. It can be warped. It's not just defined by the stuff that's in it. It controls the behavior of that stuff, and that stuff controls the shape of space and time themselves. Very profound ideas. And I'll say in a few minutes when I come to the end, something about what we understand about the nature of time as well. And maybe there is something we have yet to figure out properly. Very briefly, I will say something about quantum mechanics, because that's my area. I've spent my whole research career using quantum mechanics in my daily life, not my daily life, my daily work. First as a nuclear physicist, and now working in areas of the foundations of quantum mechanics and applying quantum mechanics to biology. It's, as I've mentioned before, it's a powerful theory. It describes the world of the very small. This picture depicts everything about quantum mechanics I can think of. You've got your Greek letter psi on one side. That's the the mathematical symbol describing the central quantity in quantum mechanics, something called the wave function. I won't go into what it means. And then, of course, you've got the cat, Schrodinger's famous cat in the box that's dead and alive at the same time. Anyway, this is just a pretty picture backdrop. What I wanted to say about quantum mechanics is that despite all its success, we have yet to figure out what it means. We've had quantum mechanics for nearly a century, and it's the only theory in all of science that's managed to get away with not having a unique interpretation. Now, a lot of physicists said, oh, why do you want to be worrying about interpretation? What does interpretation mean? Well, it's giving meaning to it. If you think about Einstein's theory, special theory of relativity, the mathematics of relativity had been figured out and done and dusted before Einstein by other mathematicians and physicists, Poincaré, Lorentz, Fitzgerald. These are physicists who developed the equations of special relativity. What they didn't have was the correct interpretation, the meaning of the mathematics, the narrative, the story that connects the symbols, the abstract mathematics to the real world. Einstein did that. He said, this is what the maths tells us. It means the speed of light is constant for all observers. It means that energy and mass are interchangeable and time is the fourth dimension, and so on. So he gave the interpretation to the mathematics. And he, quite rightly, is credited with the special theory of relativity. Quantum mechanics has got away with it. Quantum mechanics doesn't have a unique interpretation. The mathematics is fine. It works brilliantly. It makes predictions. Without quantum mechanics, I wouldn't be talking to you now because we wouldn't have developed, we wouldn't have understood semiconductors. We wouldn't have developed silicon chips. We wouldn't have developed computers. We wouldn't have smartphones. So quantum mechanics works and it describes the world. But at its heart, we don't have a true interpretation for it. And there are half a dozen or more perfectly valid ways of explaining the meaning of quantum mechanics, but each of them gives us a different narrative, a different picture about the nature of reality. This has been a long-standing argument in physics, going back all the way to the founding fathers. I'll give you 3 quotes here from famous physicists. First of all, this one from Niels Bohr. Niels Bohr's view was this: it's wrong to think that the task of physics is to find out how nature is. Physics only concerns what we can find out about nature. Not how it really is, but just what we can say about it. This is what philosophers would call epistemology, the theory of knowledge. Our physics is only about what we can say about the world, not about how it really is. And that led to this view of quantum mechanics that all it was a mechanism for predicting results of experiments, not for telling us what is actually going on. We could never know what is actually going on. All we can ever know is what we measure. And quantum mechanics tells us what we will see when we measure. Other physicists, like the great John Bell, said, he was very critical of this view. He said, look, to restrict quantum mechanics to be exclusively about piddling laboratory operations is to betray the great enterprise. Now, what do we mean by the great enterprise? Well, here Einstein gives us a nice definition of it. Einstein says the job of physical theories is to approximate as closely as possible to the truth of physical reality. So not like Bohr. Einstein doesn't say the job of physics is to say what we can say about the world. No, it's to describe reality itself. We may never reach that ultimate truth, but Einstein believed there was an ultimate truth. Nature behaves in a certain way, and the job of physics is to try and understand what that truth is, to get closer and closer to it. I'm quite happy to announce that I side with Einstein on this one, even though Niels Bohr was one of my great heroes and still is, one of the greatest thinkers of the 20th century. On this aspect of quantum mechanics, I think he wasn't right. So even in quantum mechanics, our most powerful and successful theory in all of physics, we're still arguing about what it means. So what hope do we have of reaching that ultimate truth, the ultimate theory of everything? I want to say a couple of things before I end. First of all, just to blow your mind a little bit more, this slide gives you an idea of the extent to which we are still so far away from having a unified theory of the universe. Because our three pillars of physics, general relativity, quantum mechanics, and thermodynamics, each give us different definitions of time. General relativity and special relativity says time is part of the physical fabric of the universe. It's a dimension. Time is the fourth dimension. It can be stretched, it can be warped, it can be twisted and squeezed by gravity. Literally, gravity can slow time down. So in general relativity, time is a dimension. In quantum mechanics, time isn't anywhere near as exotic. It's quite boring, in fact. It doesn't play much of a role. It's a number. It's a parameter. It's a number you plug into your equation of quantum mechanics. Schrodinger's equation is the famous equation describing the behavior of quantum particles like electrons. You plug in time, the state of the system at this time, and you can work out the state of that system at a later time, or indeed an earlier time. You can run it forwards or backwards. All you do is you put in the time and work out how it will evolve and give us an answer at a different time. So it's just a number. Then you have thermodynamics, which gives us a third picture. It says time isn't a dimension, it isn't a number, it's an arrow, a direction. It points from past to future. Relativity theory and quantum mechanics don't have such a directional aspect to time. Thermodynamics tells us time has a direction. Things change in one direction, not in the other. Balls roll down hills, clocks unwind, we get older, cups break and don't reconstitute themselves. Things happen in one direction, but not in the opposite direction. And so thermodynamics says time is an arrow. So these three definitions of time somehow have to be reconciled just to give us a unified picture of time before I believe we can have a complete theory of reality. Finally, my last example, this is quite a popular picture online. It depicts slices through the evolution of our universe, starting from the Big Bang, and then at different times as the universe evolves. First, as it expands, and particles, as it cools down, particles stick together to make atoms, which stick together to make clouds of gas, to make galaxies, stars, and planets, and life. But one of the big mysteries in physics, very often, I'm certainly asked, and many physicists are asked this: what caused the Big Bang? How did it start? The standard answer has always been, following Einstein, following general relativity, that there is no before the Big Bang. The Big Bang was the moment of creation of space and time. And so it's meaningless saying what was before the Big Bang, in the same way that it's meaningless to say what is south of the South Pole. Right? You get to the South Pole, once you're there, any direction you move will take you back north again. So there's nothing further south than the South Pole. Likewise, there's nothing before the Big Bang. But already physicists are starting to consider whether maybe there was something before the Big Bang. Maybe our universe isn't the only one. Maybe there is something called the multiverse, filled with a field called the inflaton field, which is expanding rapidly. And every now and again, bubbles appear in that field, with their own Big Bangs, creating their own universes. And our universe may be just one bubble in the multiverse. I quite like this picture as well. So again, the idea that there are parallel universes in a multiverse is something we don't have the answer to. And like string theory and loop quantum gravity, we don't even know how to test such an idea scientifically. How do you carry out a measurement to check whether it's right or wrong? And the way we do science follows something called the scientific method, which means these very elegant, mathematically elegant ideas nevertheless still have a lot of work to do, let alone to allow us to get to a final answer, a final truth. So I want to end then with just saying something very briefly about how we know what we know. I'll make sure I just get this right. So we've got I give 6 lessons on how science works. The first is, as I mentioned at the start, science isn't just another ideology. It's not just another belief system. It's based on what we call the scientific method. There are rules about how we reach consensus in science, how we test a theory, how we test theories to destruction. There is no, there may be vested interest in, if someone's developed their own theory, obviously they don't want to be proven wrong. But science as a whole, as an edifice, is constantly trying to knock down our current theories and replace them with something better. We're always testing our theories. They always have to be falsifiable. They always have to make predictions that we test. And so that's what makes science much more powerful, a more powerful way of reaching the truth about reality. In science, it's okay to make mistakes. That's how we learn. That's how we progress. Unlike in, say, a politician, when was the last time you heard a politician admit that they'd made a mistake? In science, it's not something to be ashamed of. It's not something to hide. We revel in our mistakes because that means, having made a mistake, we've discovered the mistake. We've moved beyond it. We've progressed. We've understood something new, something better. If we never made mistakes, we would never have progressed in science. A scientific theory has to be falsifiable. That means we have to be able to knock it down if a new piece of evidence comes along or a new observation is made that the theory doesn't predict. Then you have to, however much in love you are with the theory, you have to set it aside. And that's what distinguishes a scientific theory from a conspiracy theory, for example. For those of you who follow me on Twitter, I had a mini rant a few days ago talking about conspiracy theories, linking the ridiculous notion that somehow the coronavirus is linked to 5G networks. The difference is, you see, conspiracy theories tend not to be falsifiable. It doesn't matter what evidence you provide to attack conspiracy theory, the advocates of it will always support it and always either dismiss what you tell them or somehow assimilate it to help add credence to their theory. In a scientific theory, you have to be prepared to give it up in the light of new observations, new evidence. A scientific result has to be reproducible. It's not good enough for me to carry out an experiment and say, look, I've discovered something new, everyone believe me. No, I have to wait for other people to reproduce that experiment to confirm that, in fact, it is correct. And that's how scientific consensus develops. Scientists always choose doubt over certainty. We will never say we definitely know something. We always have to be a little bit uncertain, a little bit open-minded in order to change our minds. And finally, it's not always the case that a simple and beautiful theory is the correct one. Sometimes theories can just be very hard indeed. And sometimes we just have to work hard. And I think finding a theory of everything is going to show itself to be harder than maybe Stephen Hawking imagined. But that's what makes the quest so fascinating and so exciting. Thank you very much for listening.
Okay, well, thank you, Jim, for that fantastic talk. I'm sure everybody enjoyed it just as much as I did. We're going to now have a short break where you can go off and grab yourself a drink. And don't forget to, if you do have questions, you can submit them in the Slido. If you have enjoyed this, you're welcome to make donation at the PayPal link, which you can see just below the video here. We're going to go for a 10 to 15 minute break. We'll be back at 10 past 8 for the Q&A. So we'll see you all then. Welcome back, everyone. I hope everybody has had a chance to get themselves a drink, to relax, and to get ready for the questions. We can see there's been some fantastic questions already asked at the question link. You can see the link at the bottom of the screen there on slide.do with that code. We're going to hand over to our speaker, who's going to both read your questions out and then answer them. And that should help us make this as smooth as possible. So if you are enjoying it, feel free to carry on asking questions there and upvoting the questions that you'd like answered. If you've enjoyed this a lot, you can see the PayPal link just over there. That'll help us with a small donation to keep this going. And without further ado, I'll hand you back over to our speaker for this evening, Professor Jim Al-Khalili.
Okay, thanks very much, Marsh. Apologies then, people, if there was a bit of a delay, again, between me jumping in. I think a lot of people must be streaming at the moment or watching National Theatre live on YouTube. So apologies, we don't have my face, my picture, but I'm going to read all the questions and answer them as quickly as I can to get through as many as possible in the next 15 minutes or so. So the first question comes from Claire, who says, what current mystery in physics would you most like to see explained? Well, I guess really, if I'm going to be honest, it's to find the correct interpretation of quantum mechanics. That's been the bugbear of my life, career in physics, that we still don't know. There are all these different interpretations of quantum mechanics, many worlds interpretation, hidden variables interpretation, spontaneous collapse interpretation, cubism, the Copenhagen interpretation. One of them has to be right. They can't all be right. So the mystery for me is, what is the correct interpretation of quantum mechanics? Okay, next question from Andy. Jim said that things behave very differently at the level of the very small. Is there a concept of a threshold between the big and the small? Yes, there is. The transition, the boundary between what we call the quantum world and the classical world being the world of the large, is something we are still trying to understand. How does it transition? How do we go from things that are fuzzy and probabilistic and wavy, this is the nature of the quantum world, to the solidity and definiteness that we can see at our size? It's a moving scale. It depends on what you're measuring. Also, it's not a sudden sort of jump between quantum and classical. There's a sort of a fuzziness about it. How does the quantum world become the classical? The real answer is that it's something we're still trying to figure out. We're still trying to understand something called the measurement problem. How does the classical world interact with the quantum world and bring about definiteness? It's tied in again with what is the correct interpretation of quantum mechanics? So, watch this space. Okay. Phil Cheetle from Bristol says, does physics rule out people's free will? Yeah, that's a nice one, isn't it? Okay. Regardless, so I would say my view is that we live in a deterministic universe. So cause and effect, things are determined by things that happened before them in the past. And determinism means the future is already, in a sense, decided. Fate is already, it's fated to happen in a certain way. The thing is, we can never predict the future. The universe is far too good. We can't even predict if it's going to rain next week. We can't predict the future of the entire universe. So we can never know it, but in fact, it's already settled. So my view is, we don't have free will. We have the illusion of free will only, but that's sort of good enough for me. To have to think that I have free will is enough for me to have ethics and morals and so on. But from a purely physics perspective, no, it says free will can't exist. Andras Pinter from the Hungarian Skeptics. Hello, Andras. You ask, with so much about the universe unknown, how sure can we be about the laws of nature being universal? Can there be different laws in action in some parts of it? Well, it's possible, of course. But so far, we don't think so. Every direction we look around us in the visible universe, certainly, as far out as we can see, which is the light that has reached us after traveling for over 13 billion years, the boundary of what we could possibly see, everything is pretty much the same as it is here. The universe looks the same, behaves the same, as far out as we can tell. But that doesn't rule out maybe different laws in action, different values for the fundamental constants of nature, like the speed of light, in other parts of the universe. Or indeed, if there are parallel universes in the multiverse that may have their own laws of physics as well. So again, this is almost metaphysics. We can only know what we can test and check. And so far, everything seems to be obeying the same laws of physics. But we don't know what we can't see. David Good asks, what is the biggest, most surprising change in physics since your days as an undergraduate? Well, so I graduated in 1986. So certainly before the discovery of dark energy. The Large Hadron Collider hadn't been built, but the CERN particle accelerator was certainly in existence. There haven't been that many surprises. I mean, I think the surprise is that there haven't been many surprises. the most surprising thing about the work at the Large Hadron Collider is that we haven't discovered any new particles since the Higgs. So I suppose that's the most surprising change in physics, is that not that much has changed. Okay, question from Anonymous. The idea of applying quantum mechanics to biology sounds fascinating. Why, thank you. Can you tell us what it is you're doing and what aspects of biology you're looking at? So quantum biology is a speculative, many would argue controversial, new area of interdisciplinary research. It brings physics, computational chemistry, and molecular biology together in this new field. It was discovered 10, 20 years ago. There are certain experimental results that strongly suggest that inside living cells, there are things that are going on that we can only explain using quantum mechanics. Now, this doesn't mean that, all life is made of atoms, and therefore, of course, it has to be quantum mechanical, because everything is made of atoms. Everything, if you burrow down deep enough and small enough, you'll hit the quantum world. But no, there are some, the weirder, non-trivial, more counterintuitive aspects of quantum mechanics, like quantum entanglement, the idea that two separated particles can be somehow an instantaneous connection. Quantum tunneling, a particle can move through an otherwise impenetrable barrier, like a ghost going through a wall. Those aspects of quantum mechanics, which physicists and chemists have been used to, because we see it all the time in our experiments, it looks like they may also be going on inside living systems. So my research area is doing the mathematical modeling, working in an area called open quantum systems, to try and understand how these quantum mechanisms, if they are real, how do they survive? How do they work inside living systems? And ultimately, do they play a role in life itself? Okay, Matt from Bristol Skeptics says, does the multi-worlds interpretation of quantum mechanics qualify as a scientific claim? Well, it certainly does qualify as a scientific claim, in that it claims there to be other worlds, other realities running in parallel with ours. That's the way the many worlds interpretation explains the mystery, the counterintuitiveness of the quantum world. Whether it's the correct interpretation or not, we don't know, because we've not designed an experiment that can discriminate between the different interpretations. So we don't have an experiment that can tell us whether the many worlds interpretation is right or wrong. Now, some physicists who work in the area would say it's the most obvious, it's the most beautiful, surely it must be the correct one. There are others who will say, no, if you're going to give me an infinite number of parallel worlds, that's too much to swallow. And I'm not prepared to take that interpretation. So it's a scientific claim, but we don't yet know how to test it. Okay, Tom asks, do you think it's collaboration or competition that leads to the greatest discoveries in physics? In physics, I think, I would say it's more collaboration than competition. Certainly in other areas where there has been, there's been a race, particularly, let's say, in areas like genetics, different research groups around the world, because they know, that someone else is going to get to the prize, the discovery before them, that to get their publication, their paper in first. I think in physics, particularly in sort of the foundational area, the big areas of physics, it has to be collaboration. You can't have competition with something like the Large Hadron Collider, because that's an example of a laboratory where all nations have to work together. It's too expensive to be competing against each other. They all have to pitch in together. The same with the big projects in astronomy. You can't have a competition. You have to have collaboration between countries. Okay, how are we doing for time? Now, 6 minutes. John Robinson says, our solar system. It's possible, because we can never in science be absolutely certain about anything. I won't bet. My wife once told me off for betting the mortgage on some discovery in physics. Don't do that. You may just be wrong. But I would probably bet a small amount of money, not much, that no, certainly within our visible universe, all the galaxies we see all behave exactly as we would expect normal matter to behave. The light coming from them and everything that we understand about them suggests they're very similar to our own. Okay, question. Anonymous, how does quantum physics explain consciousness in the brain? Is it something about superposition collapse in microtubules? Or Dr. Sam Brooks? I'm afraid I don't know. Dr. Sam Brooks is what he said. But anyway, my guess is no. This was very popular in the 70s in the hippie movement. I think a lot of physicists were sort of high on LSD and decided that quantum mechanics was weird, man, and it explains everything and explains ESP and it explains the paranormal. Obviously, consciousness isn't the paranormal. Consciousness is real, but I think because consciousness is mysterious and quantum mechanics is mysterious doesn't mean the two are connected. Now, there have been suggestions that talks about the collapse of these microtubules, these proteins inside the neurons in the brain, when each of them can exist in a different shapes, and when enough of them to get together, then that collapses and that switches on consciousness. It's a nice idea, but we have no strong evidence that is what's going on. It may be that quantum mechanics explain consciousness, but let's walk before we can run. Steve asks, you said dark energy is something that people aren't quite sure what it is, but your colleague is an expert in it. What level of knowledge is there at the moment? Well, actually, the colleague that was the expert, the one who suggested my book should be called The World According to Jim Al-Khalili, he's an expert in dark matter, not dark energy. So if that's what you mean, we know that dark matter exists. We're not in much doubt that it's really there. There are a number of postulated particles that we think it's made of. So-called supersymmetric particles. There's also things called axions and WIMPs and sterile neutrinos. None of these particles we know for real actually exist, but they fit the bill, right? To explain dark matter. The hoped for sort of successful discovery is to find one of these particles, and then that would tell us, whether or not that's what dark matter is made of. But with the level of knowledge at the moment is we're still trying to design experiments to find the constituents of dark matter. Okay, let's see if I can get through quickly the last few. Matt asked, recently there's been a dramatic increase in the number of scientific papers published prior to peer review. Is this good or bad? Well, I mean, physicists have always published their what are called preprints on a preprint archive, and very, very often that's a good way of getting feedback from colleagues, before the paper is peer reviewed. Look, here's my paper, here's my discovery, what do you think? And sometimes the feedback allows them to improve their paper. But no, a published paper that is peer reviewed, that means it's checked by others in your field to make sure that it's valid. That is still, it's not perfect, but it's still the best way we have of trusting the results, our scientific advances that we make. So it's not good to publish papers or announce discoveries before peer review, but it's certainly something people do in order to help them hone their arguments in the paper when it finally does get published. Anonymous asks, are you surprised or disappointed the Large Hadron Collider hasn't produced any results in contravention to the Standard Model? Disappointed, I guess I would say. Yeah, it would be nice if the LHC had come up with a result that suggested the Standard Model was faulty, because that's what we all want. We don't want the status quo. We don't want these box ticking discoveries that tell us what we already knew. We want it to tell us what we thought was right was wrong, because then it's back to the drawing board. Then it's Nobel Prizes all around. We want for there to be mysteries, even though we're looking for the answers. Okay, I think we're coming to the end of time. I'll make Rowan's question, I'm afraid, the last one. Why is it thought the answer will be simple, e.g. fit on a t-shirt? The proof of Fermat's last theorem wasn't. Thank you, Rowan. That's a very good point. I agree with you. I do not think the answer, the theory of everything, is going to be simple. I don't think it's going to fit on a t-shirt. I don't think it's going to be neat. a lot of physicists, I think, over certainly the last century, have discovered that elegant and beautiful mathematics tends to be gives us a good indication of the right direction. That people like Paul Dirac coming up with his equation, he would say, look, my equation, my mathematics is beautiful. If your experiment doesn't agree with my beautiful maths, go and do your experiment again, because it's probably wrong. But I think that's not always the case. Sometimes it just isn't simple. Sometimes it's just complicated. The theory of everything, maybe the reason we haven't got there yet is because it's not neat. It's not packaged in an equation that can fit on the T-shirt. And it may take some time before we get there. Hopefully in my lifetime, I'm not going to be the one who finds it, but it'd be nice to have some answers to some of these mysteries before then. Great. I think I should draw this to a close, and I'll hand back to you, Marsh. Thank you all very much for watching and listening. I hope you enjoyed it. And if you did, well, A, follow me on Twitter, B, buy my book. There we go, unashamedly. Thank you.
Excellent. Well, I'm sure you'll all agree that was a fantastic talk by Professor Jamal Khalili there. And I'm sure you'll all join me in giving a huge round of applause. I won't clap too loudly, else I'll be picked up on the microphone here. So I hope you enjoyed. This was our first ever Skeptics in the Pub online event. We are going to be doing these weekly at 7 o'clock every Thursday. So our next one is with Sophie Scott next week. And you can see, as we've been showing during the break and at the start, the several events that we've got coming up. We're going to try and keep you with a really good lineup of excellent speakers to keep you busy and keep you entertained during this lockdown. If you did enjoy this, you can see there's a link there for PayPal to help keep this all going. You can also follow us on Twitter and like the page on Facebook. You can see those links at the bottom there as well, and that'll keep you up to date on everything we've got coming up. So without further ado, I'll say hope you all have a fantastic evening. I hope everybody stays safe, and we will see you next time.